Greetings, chemistry students. We are going to continue today with our next lesson in Unit 7. This one's going to be on formula mass. Take a moment to review the I can statements. Today you're going to be able to determine a compound's empirical formula when given its molecular formula. And you will be able to determine a substance's formula mass and convert between the formula mass and moles of a substance. So the empirical formula will tell you the simplest whole number mole ratio of elements in an ionic compound by definition. So this is basically simplest form using a smallest common factor to scale down the numbers to put them in simplest form. The subscripts tell us how many moles of a particular ion that we have in a compound. This always refers to 1 mole. That's kind of something that we've ignored up to this point. But all of our numbers, including our atomic mass in the table, is referring to 1 mole of atoms for that particular mass. We learned the other day if there's no subscript, then the number of moles of that ion is 1. For example, H2O, we wouldn't call this H2O1. We omit the ones from our formula. Remember, 1 mole is equal to 6.02 times 10 to the 23rd of anything. It's a number or a quantity used to identify a particular number of something, similar to a dozen if you're referring to like donuts or eggs. We always buy eggs in a dozen, or donuts or bagels in a dozen. I guess you could do a baker's dozen. But that dozen refers to the number 12. So 1 mole, just like a dozen, refers to that huge number there, Avogadro's number, 6.02 times 10 to the 23rd. And we use that for quantifying atoms because they're so small. So chemical formulas and reactions we're going to write by the mole, and always in whole number moles. We're not going to see anything in the scope of this class dealing with fractions of a mole. For example, hydrogen's atomic mass is 1.0. So if we take a mole of hydrogen atoms, or 6.02 times 10 to the 23rd hydrogen atoms, we're going to have a mass of 1 gram. Seems like a lot of something to only get 1 little gram, or the mass of 1 paperclip worth. When interpreting formulas, we want to be aware of parentheses around any particular element or ion. Any subscript outside of that parentheses is going to be distributed to anything inside the parentheses and is going to multiply all the elements inside by that subscript amount. For example, calcium nitrate has a 2 outside of the parentheses. So that 2 is going to get distributed to everything inside of that parentheses, the oxygen and the nitrogen. We multiply that. So that means that we actually have 2 nitrogens, and 2 times 3 we would have 6 oxygens. The 2 does not apply to the calcium because the calcium is not inside of that parentheses, where the subscript is just outside of it. So the subscript will only apply to the species directly in front of it inside the parentheses. Okay, so identifying number of moles in a formula. NaCl is an ionic compound. There are 2 moles of ions that make up that compound. When it separates, we have a sodium ion, we have a chlorine ion. We'd have 1 mole of each. Total moles that would be in a compound of sodium chloride would be 2. We'll run through a couple examples here. CaCl2, we have 1 calcium and 2 chlorines. That would give us a total of 3 moles of ions. Feel free to pause this and try these in between here. K2SO4, potassium sulfate. We would have a total of 2 potassiums, 1 sulfur, and 4 oxygen, for a total of 7 moles of ions. Now, one that's a little bit more challenging here, we have a subscript outside of a parentheses, aluminum sulfate. We have a total of 2 aluminums. We distributed 3 sulfurs and 12 oxygens. This will give us a total of 17 moles of ions. Coefficients. Coefficients are going to come at the front of a formula. They're going to tell us how many moles of the compound or ion that we have. These are going to be written before a formula. So the subscript comes after, and it's in the lower portion of our script. Coefficients are whole numbers are going to be written before a formula. And we assume, just like with subscripts, there's no coefficient written, then the coefficient is 1. So to find the total number of ions that we have, we're going to, just like we did with the subscript in the parentheses, we're going to multiply the number of a particular ion by the coefficient. So if we say that we have 2 moles of NaCl, putting that 2 in front means now we have 2 moles instead of 1 mole. It gets distributed just like the subscript, so we now have 2 sodiums and 2 chlorines, which gives us a total of 4 moles of ions in that compound. For calcium chloride, we can kind of think of this almost like there's a parentheses around the whole thing. And that coefficient will only get distributed to things coming right after it. So 3CaCl2 gives us 3 calciums and a total of 6 chlorines for a total of 9 moles of ions. 4 moles of potassium sulfate, distributing that 4 through, we'd get a total of 8 potassium, 4 sulfur, and 16 oxygen for a total of 28 moles of the compound. And with 5 aluminum sulfates, this is going to give us a lot of moles here. So we multiply the coefficient times the subscripts. We got to do this here. And then we're going to do the same thing with the 5 here. 5 getting distributed to everything inside of that parentheses, either before or after you distribute the 3 to the oxygen and to the sulfur. So this will give us a total of 10 aluminums, 15 sulfurs after we distribute the 5 and the 3, and a total of 60 oxygens. 3 times 4 is 12, 12 times 5 is 60, for a total of 85 moles of ions in that compound. How do we know some of these numbers? Like what elements are actually in a compound? Well, we can do qualitative analysis. Spectrometers help us to figure out through light, basically, what type of elements are in a compound. How is that compound absorbing or transmitting light? We can use quantitative analysis to figure out how much of each element is in the compound, to figure out what the ratio might be. Decomposition reactions are good for this, as they break down compounds into their component elements. This is how we figured out if we apply electricity to water, we get 2 moles of hydrogen and 1 mole of oxygen. So we know that that's a 2-to-1 ratio. When we collect those gases, we'd collect twice as much hydrogen as we would oxygen. So that gives us a quantitative value for how many of each element, in this case hydrogen or oxygen, are in our compound. Molecular formulas indicate the total number of atoms that each element needs to form the molecule. So this is not an empirical formula. This is a molecular formula indicating the actual amount that we need to form the molecule. Remember, molecules are the particle that results from the covalent bonding of nonmetal atoms. For example, the molecule of benzene contains 6 atoms of carbon and 6 atoms of hydrogen for a molecular formula of C6H6. If we were to simplify this, let's say we were to simplify that by dividing out a 6, this would become CH. And we'll talk about that right now, which is the empirical formula. It represents the simplest ratio in which the atoms combine to form a compound. We often use these to represent ionic compounds, which will form crystals of alternating positive and negative charges. Remember, it's a very polar bond. And that's done instead of forming separate distinct molecules. So calcium chloride is ionic, and the formula as we can see, represents a ratio of 1 to 2, 1 calcium to 2 chlorine. So if we have a sample of a calcium chloride crystal that contains 3,000 calcium 2 plus ions, then it's automatically going to contain 6,000 chlorine minus 1 ions, twice as many, given that formula. We can apply that not only just a number, but with moles. So if the crystal contains 1 mole of calcium ions, then it's also going to contain 2 moles of chlorine ions. So any ionic compound is going to be an empirical form. Calcium chloride is a 1-to-1 ratio, or excuse me, potassium chloride is 1-to-1 ratio, calcium chloride is a 1-to-2 ratio. Aluminum sulfate is a 2 to 3 to 12 ratio if we consider aluminum to sulfur to oxygen, none of which can be simplified any further. We can't break down that compound into simplest forms any further. Some molecular compounds cannot be simplified. For example, methane, CH4, can't be simplified any further. Its molecular form is the empirical form. Same thing with NO2 or H2O. They're already in simplest form. So the molecular formula is also the empirical formula. Other ones, as we saw with benzene, can be simplified. 6 to 6 ratio, if we divide out a 6 here, we'd get a CH formula. C4H8. If we divide out a 4 here, we're left with a simplified ratio of 1 to 2, giving the empirical formula of CH2. This isn't actually the same thing as C4H8, but it is a simplified version of that. Would still be 2 different substances. In this case, not that CH2 would actually be its own thing, but it is a simplified version. It is not considered the actual molecular formula. So let's figure out here, is this molecular or empirical? Feel free to pause this and check your answers as you go through. C2H2 is molecular. This could be simplified to CH by dividing out a 2. NaCl, it's ionic. Can't be simplified any further, so this must be empirical. We said this one would be molecular. Na2SO4, can we simplify that any further? No. It also contains a polyatomic ion. It's a ternary compound. So this would be an empirical form. C6H6 would be a molecular form. This could be simplified down to CH, similar to C2H2 above. KCl, another ionic compound, already simplified, so this is an empirical form. And Ca2Br4, this is ionic. This also could be simplified by dividing out a 2. And this we could get down to CaBr2. Alright, you should be able to differentiate between an empirical and a molecular formula. On to gram formula mass, a little more of the meat and potatoes of what we want to do here. Stoichiometry is the study of quantitative relationships that can be derived from chemical formulas and equations. So, we know that the mass of 1 mole of atoms of any element is equal to its atomic mass in grams. That we get from the periodic table. This is called the gram atomic mass of the element. We also just call it the atomic mass. It's read directly off the periodic table and we round it to the nearest tenth. So the mass of 1 mole of molecules or formula units is equal to the sum of the gram atomic masses or the atomic masses of every atom that makes up 1 mole of a particular molecule or formula unit. This number represents the gram formula mass, which we also call just formula mass. So you'll see that in both ways. I generally refer to it as the gram formula mass or GFM. So let's see how we do this. To determine the gram formula mass of potassium chloride, We count up the total number of atoms that we have of each element, and we look at the atomic mass from the table. So potassium's is 39.1, chlorine's 35.5. We have 1 mole of potassium ions. So we multiply 1 times 39.1. We get a total partial contribution here of potassium of 39.1 grams per mole. We add that to the contribution of chlorine, 1 mole of ions times 35.5 grams per mole each, which gives us a partial contribution of 35.5 grams per mole. We add that up and we get 74.6 grams per mole, which is our gram formula mass for KCl. So we're multiplying the number that we have from our formula, in this case 1, by the mass of that particular element, and then we're adding the totals together. Calcium nitrate. So we're going to kind of combine in figuring out our moles of ions here with the atomic mass. We have a total of 1 calcium here. We have a total of 2 nitrogens and a total of 6 oxygens. Oxygen's atomic mass rounded to 16.0, nitrogen's rounded to 14.0, and calcium is rounded to 40.1. We multiply the number of moles, in this case 1 calcium times its atomic mass from the table, our 2 nitrogens times nitrogen's atomic mass, and our 6 total oxygens times the atomic mass for oxygen. We add up our totals and we get the gram formula mass for calcium nitrate. That's 164.1 grams for every mole. And that's for every mole of the compound calcium nitrate, which includes 6 oxygens, 2 nitrogens, and 1 calcium. Another example here, aluminum sulfate. Again, we're trying to figure out how many moles of ions that we have. We have a total of 2 aluminums here. The 3 is not getting distributed because it's not inside the parentheses. The 3 will get distributed to the S and to the 4 oxygens inside, so we get a total of 3 sulfurs and 12 oxygens. Our atomic mass of aluminum gets rounded to 27.0. Sulfur gets rounded to 32.1, and oxygens gets rounded to 16.0. We multiply each of these, add them together, we get a total for our gram formula mass of aluminum sulfate, which is 342.3 grams per mole. Now we're going to have to be able to convert back and forth between moles of a substance and the mass of that substance. So to convert grams to moles, we're going to divide the formula mass. We're going to divide by the formula mass. So we have a given amount over the gram formula mass, and this will tell us the number of moles. And this is on table T with each of our other equations. This is our mole equation. So how many moles of KCl are there in 182.9 grams of KCl? First, we find the formula mass of KCl, which we did prior, which was 74.6 grams per mole. This goes in here as our gram formula mass. So this is going to be the lower part of our formula here on the right. And the amount that we're given is 182.9 grams of KCl. And this here is going to be moles of KCl. And that's equal to 182.9 divided by 74.6. And this gives us a total of 2.45 moles. So that 182.9 grams is equal to almost 2.5 moles of potassium chloride. How many moles of potassium oxide are there in 220.4 grams of K2O? The steps are listed here. Why don't you pause the video, and try the problem. First, we find the formula mass. I don't think I did that there. First, we find the formula mass. We have 2 potassiums listed here. We have 1 oxygen in our formula. We're going to multiply this times 39.1 grams per mole. And we have 1 oxygen that will multiply by 16.0 grams per mole. This is going to give us a total of 78.2. And this will give us a total of 16 grams per mole. We add this up, and we get 94.2 grams for every mole of K2O. Now to figure out the moles. We have 220.4. So for step 2 here, we're going to plug in here our given mass, 220.4. We're going to divide that by our formula mass, our gram formula mass of 94.2. And this will give us a total of 2.3 moles. To convert from moles to grams, we're going to multiply by the formula mass instead of dividing. So we'll do a couple examples here of this. We know the formula mass of KCl is 74.6 grams per mole. If we're given 2.45 moles, what would be our given mass? So we multiply this by the formula mass and the number of moles, and we get a total of a given mass of 183 grams. We'll be doing lots of practice with this in class. Make sure you bring questions with you when you come. Have a wonderful day, everyone.